Hello and welcome to this second lecture on quantum error correction. In the first lecture we looked at the repetition code, which is a nice simple classical method for error correction. We can use it to detect and correct either bit flips or phase flips when implementing it using quantum gates. However, in quantum error correction we need to be able to do both at the same time, and so it's not a good quantum code. The surface code is a good quantum code, and so we're going to start looking at that today. But first, let's dwell a little bit more on the kind of measurements that we did in the repetition code. So first, let's remind ourselves of the Bell basis states, the lovely Bell basis states. We have phi plus, which is correlated in the Z basis. So we have the superposition of the two even parity states for the Z basis. For the X basis, we can also write it as a superposition of these two even parity states, so it's also correlated. For phi minus, it is correlated, and so even parity in the Z basis, but anti-correlated in the X basis, and so odd parity. In the psi plus state, we have this superposition of the two odd parity states in the Z basis, so it's anti-correlated, and we have the superposition of the two even parity states in the X basis. And for phi minus, it is anti-correlated, and so odd parity in both. So we have all of these combinations of odd and even parity in the Z and X basis expressed in all of these Bell basis states. Now, the parity measurement we looked at last time was aiming to distinguish between the subspace spanned by the two even parity states and the subspace spanned by the two odd parity states. So this means that if we had 0, 0 or 1, 1 or any superposition of those, then the parity measurement gives us the outcome 0. And importantly, if we do have a superposition, it does not disturb that superposition because it's not extracting any information about the states that are inside that superposition. It's extracting some information that is true for both of those states, and so it doesn't care to disturb the superposition. Similarly, if we had 0, 1 or 1, 0 or any superposition thereof, we would get the outcome 1, but those superpositions would not be disturbed. If we had a superposition of even parity states with odd parity states, then it would have to choose between the two and disturb the superposition. But if we just have even parity states, it outputs a 0, superposition's fine. Odd parity states, outputs a 1, superposition's fine. And that means that similarly, if we were to have the state phi plus and we were to do one of these measurements, it would tell us 0 for even parity, and then we would just still have the state phi plus. Similarly, if we had phi minus, it would give us the outcome 0 because both of these states are superpositions of the even parity states, so they also span this even parity subspace, and so we would just have the state phi minus, we would get the outcome 0, we would be good. Similarly, the psi plus and psi minus states, which span the odd parity subspace, would give us the outcome 1, but we would still have those. So we can think of this parity measurement as being, it looks at whether we've got 0, 0 or 1, 1, and if we have either of those gives us a 0, or we can think about it in terms of the Bell basis as well. Both are equally valid. Now, with measurements we can often think to write down an operator which corresponds to that measurement. So for the Z measurement we have the Z. So a Z measurement is measuring whether we are in the state 0 or 1, and the Z is a operator which has 0 and 1 as its eigenstates. And of course the Z measurement distinguishes between whether we've got 0 or 1, and the Z operator distinguishes between the 0 and 1 eigenstates by giving them different eigenvalues. We have the eigenvalue of +1 implicitly here for the 0 state, the eigenvalue -1 for the 1 state. So we use plus and -1 as the eigenvalues and 0 and 1 as the bit values that we get as the result, which is a bit weird and inconsistent, but oh well. Similarly, for the X measurement, we have the eigenstates plus and minus, and they're distinguished by different eigenvalues as well. And also, one thing that we know about X and Z measurements is that they are complementary. And so if you were to do a Z measurement, then it would give you a state which is a definite result for a Z measurement. So you would measure it, you get 0 or 1. If you get 0, you would know that your state is in the state 0 now. If you were to measure it again, you would get the outcome 0 with certainty. But if you were to measure x at that point, then x can be expressed as 0 can be expressed as a superposition of plus and minus. So you would randomly get plus or minus, and whichever it chose, say minus, it would be minus then forevermore. If you were to measure x more times, you would keep on getting the outcome minus until you were to, say, measure z again, where you would get a random outcome of 0 or 1, and so it would continue. So basically z measurements and x measurements are fighting against each other. When you measure one, it messes up what the outcome would be for the other one, and that's because they have different eigenbases, and even more strongly than this, they anti-commute, which means their eigenbases are, well, very dissimilar. However, if we think about the operator that could correspond to the parity measurement that we've made, well, we can have one that has, well, eigenstates 0, 0 and 1, 1, of course, because these are the states that we often describe this measurement in terms of. But both of those correspond to the same outcome. So we're not going to give them different eigenvalues, we're going to give them the same eigenvalue. And the other states are 0, 1 and 1, 0. They are going to have different eigenvalues from the even parity subspace, but they're going to have the same eigenvalue as each other. So we have this plus 1 eigenspace, as we call it. It's the space spanned by the 0, 0 and 1, 1 states, the even parity states. And then we have the minus 1 eigenspace, which is the space spanned by any state that can be considered as an eigenstate with eigenvalue minus 1. And so if we have any state which is an eigenstate of this with eigenvalue plus 1, then we just get the outcome 0 and the measurement does not affect it. And if we have any state which can be expressed as an eigenstate of this with eigenvalue minus 1, which means that it can be expressed as a superposition of 0, 1 and 1, 0, then it will give us the outcome 1 and will be otherwise unaffected. But we can just equally express this in terms of eigenstates phi plus and phi minus as the plus 1 eigenspace, and psi plus and psi minus as the minus 1 eigenspace. So we don't have to think of it in terms of 0, 0 and 1, 1. We can think of it in terms of phi plus and phi minus as well, in terms of the Bell basis. And this operator actually corresponds to the tensor product of z with itself on 2 qubits. So it's the 2 qubit ZZ. So when we talk about making a ZZ measurement, it doesn't mean that we individually measure z on 2 qubits. It actually means that we measure this parity. So it can in general be an entangling measurement or one that preserves entanglement, because if we do a ZZ and our state is, say, phi plus, then it will remain phi plus. It won't get collapsed down into just zeros and ones as it would if we did individual Z measurements of both. Similarly, we can write down an XX measurement, and this is expressed naturally in terms of plus plus and minus minus as the plus 1 eigenspace, plus minus and minus plus as the minus 1 eigenspace. But we can also write this in terms of the Bell basis states. So in this case, phi plus gets the eigenvalue plus 1, as does psi plus. Phi minus gets the eigenvalue minus 1, as does psi minus. And this then defines our XX measurement. And you can see that actually these now share an eigenspace. The ZZ and the XX share an eigenspace. There is a way of writing them where they have the same eigenstates. And this means that we can actually create states which have definite values when we do either measurement, and they don't mess each other up. So if we had, for example, the state phi minus, then when we made a ZZ measurement, it wouldn't collapse that state, wouldn't affect that state, it would just say 0. And if we were to then do an XX measurement, it wouldn't mess up the state at all. It would just with definite certainty give us the outcome 1. And then if we went back to the ZZ, we'd still get the 0. So this is a fundamental difference between ZZ and XX measurements with just single qubit Z and X measurements, because we find that if we have XX and ZZ and we look at their commutation properties, then the fact that Z and X anti-commute with each other means that for 2 we will get 2 factors of -1. Those 2 factors of -1 will square, and therefore we find that ZZ and XX actually commute. So their measurements are completely compatible. We can swap between them without messing anything up. So in the repetition code, we thought of having a line of qubits, and then for pairs of qubits that were neighboring on that line, we did these 2 qubit parity measurements, which we now know are ZZ measurements. For the surface code, we're going to go up to 3 dimensions. We have a square lattice, and we define our measurements in relation to what is neighboring on this lattice. We have measurements that are made around each plaquette, as we call them. So these are the squares of the lattice, and the qubits here are the black dots. So we have 4 qubits around each square, and around those we do ZZ measurements. So here I'm using sigma Z instead of a capital Z as I've been using otherwise. It's often that people go between these 2 conventions, so there's no need to get too confused, but they're representing the same thing, which is a Pauli Z. So we have these ZZZZ around the qubits of the plaquette, so we're making a 4 qubit parity measurement. Now at the top and the bottom we have these sort of truncated plaquettes that only have 3 qubits. So what do we do with those? Well, we just make 3 qubit parity measurements. And also on the vertices, we have 4 qubits around each vertex, and on those we make 4 qubit parity measurements, but this time in the X basis, so XXXX. And for the sides where we have these truncated vertices, we do XXX parity measurements. So these are the measurements we're going to make. Why do we do that? How is it useful? Well, let's continue and we'll see. So let's first focus on the Plaquette syndrome, and actually we're going to go through all of the steps of how this quantum error correction scheme works, but only with the Plaquette syndrome to see how it detects and corrects bit flip errors. So these are similar to the 2 qubit measurements in the repetition code, where we make 2 qubit ZZs, and the circuit that we use is very similar. It's just we do it controlled on 4 qubits instead of just controlled on 2. So here we have our IJKL, which is what I'm calling the 4 qubits around the plaquette, and we do our controlled knots controlled on each of those 4 qubits and targeted on an auxiliary qubit that we can think of as living in the middle of the plaquette. And if there's an even number of 1s around that plaquette, as we see here, then only 2 of those controlled knots will actually flip the auxiliary qubit. Sorry, an even number will flip the auxiliary qubit, which means it flips back to its original value of 0, and that's what we get as an outcome. Whereas if there's an odd number of 1s, we get an odd number of flips, and so we end up with a 1 at the end. So far, so normal. So let's think of defining a classical code now, which uses these Plaquette syndromes to detect and correct bit flips. And so we're just going to be classical so far, although we're going to make this quantum later. So let's define a valid state. So one of the states which, when we make the syndrome measurements, we think, oh right, everything's okay, that's good. And so in the case of the repetition code, we associated the parity measurements having an outcome 0 as being the case where everything is good, and the parity measurements having an outcome 1 as being a clue of an error. So let's use that again, and we're going to try and find states for which there is a outcome of 0 for all of the parity measurements, and that is going to encode one of our logical states. So what's the easiest case where we can have an outcome of 0 for all of our parity measurements? Well, we could just have zeros everywhere. That's even parity. So all of our plaquettes will tell us that we have even parity. And what logical value can we store with this? Well, if we're storing a bit, then we're storing 0 or 1. And it kind of makes sense that zeros everywhere should be associated with 0. So let's do that. Now what we can note from this is that there are lots of nearby states, as we can call them, that also have even parity on all of the plaquettes. So for example, if you just flipped 4 bits around this particular vertex, you would get another state which, when you look around each plaquette, you have an even number of ones, so that's even parity. So this state should not be associated with our logical 1 because it is very close to our logical 0. You only need to flip 4 bits in order to get from one to the other. And making the code bigger is not going to make it more complicated to flip from one to the other. It's always just going to be 4-bit flips away. Similarly, we can go from that to flipping these 3 bits and having something which is a little bit further away from our original state, but still quite close to a state which is quite close to our original state. We could flip another 4 bits and so on and so forth. It turns out that we get a very large family of states which are very close to each other, and so we're going to treat these all as alternative ways to store a 0. They're all going to be within a family of states which are corresponding to a logical 0. And in fact, the way we can generate this family of states is to start off with the all 0 state, pick any vertex, flip all of the bits around that vertex, and then we have a new valid encoding of a 0. And this generates an exponentially large family depending on which set of vertices you choose to flip all of the bits around. And so here we've flipped all the bits around this vertex, here we've done this vertex and that vertex and this vertex, and so on. So, the states in this family can be very different, but there is one feature they all share in common, which is that if we pick any line from top to bottom, which passes along the edges of the lattice, then it has even parity. And we can see this because any line from top to bottom will go through, well, basically goes into a vertex and then out of a vertex. So whenever we flip all of the bits around the vertex, it always encounters 2 bits that we have flipped. So it preserves the even parity. So if we go just straight from top to bottom, then we will find even parity. If we do any sort of complicated route from top to bottom, still, if it passes through vertices, it will have even parity for any of these states, which are just a vertex flip away from the all 0 state. So this gives us a clue about how to encode a 1, because if all of the states which correspond to a logical 0 have even parity when we take a line from top to bottom, then what about states which have odd parity when we take a line from top to bottom? And we can generate these by, for example, just taking a line that passes through plaquettes from left to right, and since it goes in and out of each plaquette, then each plaquette has an even parity due to this line. But if we take any of these lines that pass through edges from top to bottom, then it will intersect that once and therefore have odd parity. So we can take this as the base of our family of states that correspond to logical 1s. We can also generate an exponentially large family by doing this thing of picking a vertex, flipping all of the bits around it. Okay, so what is the logical x and z that we can perform on this logical qubit, or logical bit? Well, what is logical z? Well, we can think of a z measurement, as we said, as the measurement that distinguishes between 0 and 1. So in terms of measuring z, it is distinguishing between the subspace that corresponds to a logical 0 and the subspace that corresponds to a logical 1. So the observable is one that gives even parity to all of the family that are corresponding to logical 0, odd parity to all of the ones that correspond to logical 1. And so we can just take a tensor product of all of the sigma z's on this line, on any line from top to bottom. So we could use one side, or we could use the other side, or we could use any weird thing in the middle. I like the sides because I like to think of the sides as just being big plaquettes, but they're ones that we don't measure as part of the syndrome, but they're otherwise completely equivalent to the behavior of a plaquette, and we'll see more about why that's interesting later. Okay, so that was a logical z, or measuring a logical z at least. What about a logical x? A logical x is the thing that flips from 0 to 1 and 1 to 0. And so how do we do that? Well, we have to introduce one of these lines across the middle. And then, so taking the all 0 state, finding a line from left to right, and flipping bits will take us from the 0 family to the 1 family, the 1 family to the 0 family. And so basically we just need a tensor product of x's that passes along one of these lines. And we can do the top, or we can do them along the bottom, or we can do them along the middle, as we sort of see here. Doesn't matter. But again, I like tops and bottoms because they basically, we can think of them as a large vertex that we are not taking into account when we measure the syndrome as well. Okay, so what are the effects of errors in this? Well, if we apply an X, so a bit flip, to any of the qubits, then it will change the parity of its two neighbours. So here we've got an isolated bit flip, and so the parity of these two plaquettes is going to be flipped from their initial value, which is even, telling us that everything's okay, to odd, telling us, well, there's something going on here. And we're representing that with this blue dot. Now if you were to get a couple of bit flips close to each other, then it's like this bit flip has created these two plaquettes, or created two plaquettes which are saying something's wrong, but this second bit flip has made this plaquette actually think everything's okay again. So it's moved that hint of something being wrong, has been effectively moved over here. So we have another instance of this over here and over here, and if they were next to each other, we would have them moving horizontally or vertically. Now, one interesting case is where we have a bit flip on the edge. There, only one plaquette sees that something is wrong, and if we were using this edge to be our logical Z value, then that logical Z value would also have been flipped. So this is what I'm saying, that you can think of this as being like a big plaquette whose value is just getting flipped, corresponding to the logical value. So if we think of what would happen, what would need to happen in order to create an X error, then it's basically like you've done a bit flip here, say, and it's created these two plaquettes in which something is wrong, but you need to then do another bit flip here, which moves that hint along, and then moves it again and again and again and again and again, and then throws it off that edge where you're not looking for it. And also a bit flip here that throws that one off that edge. And then you end up with a line all the way across, and the hints have been thrown off the edge. And so this is an X error, a logical X error. Equivalently, we would actually just need to separate them sufficiently far. So for example, if we had a flip here, as we see, but also one here, 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 and we had some random hint that something was wrong over near this side, we'd probably think that we had errors here, here, and here, and should throw it off that edge to get rid of it, but that would have consolidated the error rather than correcting it. So anything that stretches more than halfway across in terms of bit flips, that would be a problem. But we have to stretch halfway across. So it's kind of like in the repetition code that we have to have these flips on more than half of the bits, but now it's, rather than just half of the bits, it's half of a path that spans from left to right across a two-dimensional lattice. So with this, we have very much like the repetition code, but just generalized to 2D for no apparent reason. And so hopefully you can see that it can correct bit flip errors and protect a bit value. So now let's move on to the Vertex Syndrome. So the Vertex Syndrome looks for parity in terms of the pluses and minuses. So one way we could do that is reverse the direction of our controlled knots and use a phase kickback effect. But here in this circle I'm just showing we do Hadamard's either side of the control, so that they're effectively controlled on the plus and minus states rather than the 0 and 1 states. And otherwise, it's just exactly the same as before. So these operators can also allow us to encode and protect a bit value. So, but this time they're protecting against phase flip errors rather than bit flip errors. So let's think how they do that. So let's associate our two values with plus and minus. And we can associate the plus state with a state which has even parity on all of the vertices. So the parity has to be done in terms of the pluses and minuses. So that can be easily done by just having plus on everything. And then we can pick plaquettes and flip all of the qubits around the plaquette from pluses to minuses, minuses to pluses, and that generates an exponentially large family of states that correspond to the logical plus. But all of them would have, if we go from left to right through the plaquettes, all of them would have even parity, and that's because any plaquette is passed into and out of by any line that goes from left to right through plaquettes, and therefore it will encounter two flips which preserve the parity. However, if we were to do a line from top to bottom that goes through the vertices and so along the edges, then it would only pass through that once, and so if we flip all of those, then we get odd parity for the pluses and minuses on a line through the plaquettes from left to right. So it's kind of like everything I said before with the Plaquette syndrome, but rotated by 90 degrees and in terms of pluses and minuses instead of zeros and ones, and any role played by the plaquettes is now played by the vertices, and any role played by the vertices is now played by the plaquettes. So that's why I'm not going into it in excruciating detail, because it's just the same again, but rotated 90 degrees, plaquettes and vertices swapped, and 0 and 1 and plus and minus swapped. Yes. So now for this encoding, what are the logical x and z? So the logical x is the thing that can distinguish between the plus and the minus states. So if we're thinking of measuring the logical x, we need to be able to distinguish between the plus and minus states. Well, as we saw on the last slide, the plus and minus states are defined by the parity when you do a line of a line from left to right that goes through the plaquettes, and it's defined by the parity of the pluses and minuses. And so we can detect that by having a line from left to right that goes through the plaquettes, which is a tensor product of x's on all of those qubits, because that gives us the parity in the plus-minus basis. If we want to flip between the logical 0 and the logical 1, that means we have to take a line from top to bottom which goes along the edges and flip pluses to minuses and minuses to plus. That's done by the Z operator, and so we need to pick a line from top to bottom that is composed of a tensor product of Z operators. And even though now we're thinking of measuring the x and performing the z as a unitary, whereas before, for the last encoding, we were thinking of the opposite way around, we find that the logical z and x that are defined by this encoding are exactly the same as they are before. So this shows us that, well, this gives us a hint of what we'll see in a minute, that these two encodings actually can be done at the same time. First, let's apply a z to any code qubit to see what the effect of a phase flip would be. Well, what it does is it flips the parity of the two vertices either side, and if we do a couple, then it basically creates a pair of hints, and then the next phase flip moves one of those hints. We can also have these effects where if you do a flip on the top or the bottom, you only get one hint because the other one is kind of being effectively changing the value of the logical operator. And also as a little hint to when we get to the full quantum case, if we do a Y, that also does a phase flip, which flips the value of the two vertices either side. And of course, as we'll see, it flips those of the plaquettes as well. So if we put it all together, this allows us to detect both bit flip and phase flip errors. So we can detect X errors, Z errors, and Y errors. Because the Plaquette syndrome detects the bit flips and the Vertex syndrome detects the phase flips. And because the XXXX and the ZZZZ of these observables that correspond to these measurements commute, then they can be done simultaneously and they don't mess each other up. And the reason why they commute is because if we look at any plaquette and we look at the vertex next to it, they overlap always on an even number of qubits. So just like XX and ZZ commute, so do all of these plaquette and vertex operations. So our encoded 0 has to be a state which, when we measure all of the plaquette operators, we get the outcome 0, And we get that by just making it a superposition of all of these states, which would give us the outcome 0 for a Plaquette operator. So because it's made up of states that are even parity for that particular plaquette, then it is also even parity for that particular plaquette. More interesting is how it is an eigenstate of the vertex operators. So it also has to be such that when you measure any of the vertex operators, you get even parity. So that means it has to be a +1 eigenstate of the vertex operators. And if you think of, say, this vertex here, then if you were to apply the vertex operator, it would take this state and turn it into this state, and it would take this state and turn it into that state. And so it's just permuting them in the superposition. And on those two, on that little superposition of those two particular bits, then it doesn't do anything. Similarly, everywhere else, you're just going to get permutations of things that are already in the state, so it doesn't actually affect the state. So this big superposition is indeed an eigenstate of all the vertex operators with eigenvalue +1, and therefore when you measure them, you're going to get the outcome 0. Okay, so what are the Z and X operators for the qubits stored in this code? Well, they're exactly the same to the X operators that we've just been looking at so far because of this consistency between the two encodings. And so we can do these fault tolerantly because it just means between two syndrome measurement rounds we run across with a bunch of Z's, we run across with a bunch of X's in the other direction if we want to do an X. The Hadamard can also be performed fault tolerantly. It's not quite so obvious how to do this, but what does the Hadamard do but map X's to Z's and Z to X's? So one thing you can actually do is take the code and rotate it by 90 degrees so that now lefts and rights become tops and bottoms. And the only other thing to do is swap the roles of zeros and ones and pluses and minuses, which can be done by just Hadamarding everything, relabeling your plaquettes as vertices and your vertices as plaquettes. So that can also be done fault tolerantly because it's mostly just, well, these rotations are a bit weird. But it's kind of classical relabelings of where you consider things to be and whether you consider things to be plaquettes or vertices. And the only quantum stuff is actually Hadamard on everything, which you do between syndrome measurement rounds. And you adjust your syndrome measurement such that that doesn't mess everything up. Yeah, Hadamards are weird, but they're also fault tolerant. So obviously here we need highly entangled quantum states. The logical 0 is a highly entangled quantum state. The logical 1 is a highly entangled quantum state. Any superposition of them is a highly entangled quantum state. And they're actually examples of something called topologically ordered states, which are quite an exotic form of many-body entanglement. Aren't these things hard to make? Well, the thing is that the measurements that we make in order to detect errors naturally will create and sustain them. So even though it is hard to make a big lattice and to do these measurements with sufficient accuracy in order to really sustain this, and this is something we're working towards, once we get those things in place, it will become super easy to sustain them. Yeah, so as we said last time, any error can be thought of as a superposition of X and Y and Z and nothing. So if we think of a general error being applied to this, it will actually create a superposition of no error, or a bit flip error, or a bit and a phase flip error, or just a phase flip error. And when we measure the syndrome, it collapses it to one of those possibilities. So complex errors just become essentially Pauli noise. It's a little bit more complicated than that because here we're just actually applying noise to one qubit. So it very much just collapses down to Pauli noise. If we applied our noise to all of the qubits, then we might get interference effects going on, which cause everything to be a little bit different. But basically, we are collapsing everything down to Pauli noise and correcting it accordingly. Also, how do you make the readout at the end when you want to get your logical 0 or 1 out? Well, we would need to do this fault tolerantly. And if you were to measure a 0 or a 1, say, if you were to measure your logical qubit in their logical Z basis, and what you can do is just measure all of your code qubits. And you don't care that that collapses the superposition and destroys the entanglement because this is the moment of readout. You're just getting the 0 and 1. And then if you wanted to recreate it, if you wanted to continue on in your computation, you could just re-encode a new 0 or 1, depending on what outcome you get. So when you do this readout, what you find is that you get, well, the values of all of the qubits, and this can be used to deduce one final set of syndrome measurements by going around all of the plaquettes, and also it can be used to find the final eigenstate, like the final parity on a line from top to bottom. So you get a final syndrome measurement and you get the parity of your logical operation. You don't get any information about what's going on the vertex stabilizers because you've made single qubit Z measurements, but you also don't care because they commute with. So any error that would be picked up there is an error composed of Z's, which actually commutes with the observable that you're reading out. So they wouldn't have any effect on the final readout anyway, so they don't need to be detected or corrected at that particular point. So if you have measurement errors, which mean that some of these are lying, it's exactly the same as there being a bit flip just before the measurement, and those bit flips are detected and corrected using the standard ways of this code. So it's all good. Right, now we move on to decoding, which is after we've detected where the bit flips are, how do we actually work out how to correct them? So we can't just do a majority voting here as we could in the repetition code, we have to do something more complex. Now we don't actually need to work out what errors happened, but we need to work out the equivalence class of what errors happened. So here, for example, we can have a case where we had two phase flip errors causing these two hints diagonally. And if someone were to come along and look at these two hints and think, well, what happened? Then they might deduce that it most likely was just a couple of phase flips here, but it could equally have been a couple of phase flips here. Which was it? Well, there's no need to actually care about that too much because if you choose correctly, you do a couple of phase flips that cancel out the original ones and it's all good. If you choose incorrectly, then what have you done? You've had a couple of Z's in error here and here, and you've done a couple of Z's in order to try and correct this, and overall you get Z, 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 Z. What is Z, 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 Z around the plaquette? But one of these plaquette operators. The states that we have are eigenstates of the plaquette operators, and so they act as if they were 0 anyway. If we have isolated errors like this, it's easy just to work out where the error happened and undo it. And here, if we had a couple of big errors next to each other and we thought that they were actually these smaller errors, then this just corresponds to the product of a couple of plaquette operators. Again, we're in an eigenstate of that. It's all good. The problems come when we have more errors, and it's easy to get mixed up between what's going on. So here we have a whole bunch of errors that stretch almost halfway across, and so our best guess at what errors happened is maybe there was a bit flip here that caused that one in isolation, and maybe there was a bit flip here that caused these two, a bit flip here that caused these two. Actually, it was bit flips here and here, and so we deduce something that is different from what is real by a line of phase flips that goes from top to bottom. And so rather than all of our mistakes in decoding producting together to be just plaquette operators, they product together to be plaquette operators and a logical Z, and so we have caused a logical error. So we always want to be able to find the equivalence class where if you multiply the errors with what we've done to correct them, you get just a product of plaquette operators, and we're in an eigenstate of those, so it's all good. What we don't want to get is the other equivalence class where it's a product of plaquette operators times a logical operator, because that means that we have in error caused a logical operator to be applied. So one option for this is minimum weight perfect matching, and we actually already talked about that last time for the repetition code. In fact, when we went to from the repetition code to having a time element to take into account imperfections in measurements, then we use minimum weight perfect matching. We can do it in exactly the same way here. So for example, you've got these two, you've got these two. What errors caused these two? You've got to try and work out what could have caused this set of hints with the minimum amount of errors. And you can think of that as well as an edge that connects these with weight 1, an edge that connects these with weight 2. You'd need 1, 2, 3 phase flips to connect those two, so that's an edge of weight 3. And then you try and pair them up in a way that has a minimum total weight corresponding to a minimum total number of errors causing this. So we can also do the decoding for the X errors and the Z errors independently by an independent matching procedure. Not necessarily the best way, but it's a way. We also do need to account for the effect of the edges, and we can do this by introducing virtual nodes. This is actually also required for the repetition code, but we ignored it earlier. So for example, if you've got a case where you've got a single hint up here near the top and a single one down here, then if you've not accounted for the effects of the edges, the only two nodes on this entire thing are those two. So you might think, well, let's connect them. But that would mean that you would try and correct it by doing Z, 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 almost all the way across the grid. And it was most likely Z's here and here that caused the error, so you've caused the logical operator. Don't want to do that. And so you have a couple of virtual nodes corresponding to what could be the other side of them if there was an error off the edge. However, you've also got to account for the fact that if there wasn't an error off the edge, those nodes have to be matched to something, so you match them to each other with weight 0. So in this case, if we had these two nodes and they were caused by errors, or most likely caused by errors near the edges, then we connect those to their virtual nodes by 1, because that's the number of errors to connect it with an edge, and to each other with 6, and we connect these two with 0. But the minimum weight matching is for us to pair these and to say there's 2 errors that could have done this. However, if we had these nodes nearer the middle, and they're most likely to have just been created with each other, then these edges that connect them to the edges are much larger, and so we have a minimum weight which is taken by pairing these two, getting the weight 0, and then pairing the two virtual nodes to each other. Pairing these two, getting a weight 2, and pairing these two virtual nodes with each other to get a weight 0. Now if we have imperfect measurements, then again we're going to have the fact that the measurement might lie, and that's going to be a problem. So for example, if we had somewhere where we think there is no hint of an error when actually there is, just because the measurement result was bad, then that could completely mess up our decoding. So we don't want to do that. And the way we do it is just in the same way as the repetition code. We use syndrome changes over time as our hints of errors. That tells us both about errors that actually occur on the code qubits, but also about these sort of imperfect measurements. And then we just extend our minimum weight perfect matching to 3 dimensions, and there we go, job done. The idea is to try and get a threshold, and so a threshold means that if we plot the probability that our decoding goes wrong against the probability that errors happen, so you could take the little p here as just being a probability of bit and phase errors on each qubit, the probability of a measurement lying. If we plot the probability that things go wrong against this little p, what we expect to see is that the higher the probability that things go wrong, the higher probability on each qubit, the higher the probability that our decoding will fail overall. But what we want is that if we increase the size of our code, things will be better. So if we plot this for a larger code, we would expect the probability of getting things wrong to be smaller. But also we have to think that for a larger code there is more to go wrong. There are more qubits, more places that an error can happen, more probability that a big horrible error string will occur, because with the repetition code we needed half of the bits to be flipped, and there's a certain binomial coefficient in the terms of how many different halves there are, which increases as we increase the size. But if we've now got 2 dimensions and we've got all of the possible ways of going across, then that's an even bigger binomial coefficient. So actually, when things are really bad, when errors are very likely, then the size of a code will actually be worse because there's just more places for errors to happen. So we would find for our bigger code, actually at some point, the probability of things going wrong would be larger. And between those 2 points, there is a crossover between these regions where things get better with bigger size and things get worse with bigger size. And there's some scaling laws about how this crossover point moves a little bit. But in general, we can just think there's a crossover point, and if we increase the size of our code to infinity, then we're basically going to be in a region where the probability of a logical error is 0 until it suddenly becomes big. And this is the threshold. So the threshold is the value that we're trying to attain. We need to get our probability of noise below this threshold, and then we can just build bigger and bigger codes to make the probability of a logical error as small as we like. And the threshold is going to depend on our code, but also on our decoding method, and also on the details of the noise model. So, we've seen how to do logical X, logical Z. You can do a logical Y by doing both of them. I've talked briefly about how to do a logical Hadamard. For a logical controlled knot, that can be done without too much trouble, because what is a controlled knot? But it does an X to 1 qubit depending on whether another qubit is 0 or 1, and whether or not a qubit is 0 or 1 in this case depends on parities. And so you can basically convince yourself, hopefully, that if you do controlled knots between all of the qubits of one code and the corresponding qubit of the other code, then it will do a controlled knot between those 2 codes. And because it acts independently on the qubits of each code, then any imperfections associated with that are just going to turn up as little single qubit errors that you correct. So yeah, you can do multiple operations. You can do other Clifford operations as well if you do some crazy tricks. However, no other logical operations other than Clifford's can be done fault tolerantly, but we do have methods to sort of inject them. So we have this thing called magic state distillation, which uses the fault tolerant gates that we have from the Clifford gates to clean up the non-fault tolerant gates that we don't, to make a fault tolerant non-Clifford. It's a bit messy. It's a bit, there's overheads involved, but it can be done. So it shows that we can do fault tolerant quantum computing with this code. But the means to do that are beyond this lecture. Also beyond this lecture is talk about anions, but let's do a little bit of it anyway. These hints that we create, when we do an error, we create this pair of hints, and these can be moved around. They're kind of like particles. And we find that they're actually a type of particle called anions. So they're not bosons or fermions, because they don't obey the exchange statistics of bosons and fermions. If you were to take one of the particles that is created on a plaquette and one of the particles that's created on a vertex, and you move one of them around another, your wave function will acquire a phase of -1, which is something that doesn't happen for bosons and fermions. It can only happen for particles that live in a 2-dimensional universe, which is what the surface code essentially is. So there's some interesting topological stuff that goes on in this code as well. Here's the maths of it that I'll leave on screen for a moment. But basically, we have done everything we need to do in this lecture. We have introduced the surface code. We've shown how it can detect and correct both bit and phase flips. We've seen how you can do logical operations. And that is what you need in order to do fault-tolerant quantum computing and run the kind of algorithms that we did in the previous lectures. So that's all for today. Thank you for listening.